Hello. So I received this problem in these terms. I want to simplify the following expression, which is a sum involving the binomial coefficients. To perform this count, right, or this simplification, what I'm going to do is incorporate some ideas. So first, some experimentation. So I want to know what happens as I vary the values of n, as I take different values of n with this expression, and in hope to get some pattern, right? So let's see. When n is 0, right, this sum actually is composed of only one term, meaning C0, 0, which of course is 1. When n is 1, this sum consists of two terms, C1, 0 plus C1, 1, which of course is 1 plus 1. When n is 2, right, this becomes C2, 0 plus C2, 1 plus C2, 2, which is 1 plus 2 plus 1, which is 4. 2 here. Take one more. So I say 3. Well, for this case, I have C0 plus C3, 1 plus C3, 2 plus C3, 3. Well, in this case, this is 1 plus 3 plus 3 plus 1, which is 8. Now, you may wonder, where is that I'm getting these numbers right away? Well, the thing is that the coefficients that we find here, right, the binomial, they're taken from Pascal's triangle. So I'll just briefly explain how is the construction associated to that. So you start with 1, and then we go row by row. Expand ones at the end, express ones at the end. And then for whatever comes in between, that should be the sum of the diagonals right above it. So the next row should be 1, 2, 1. The next one to this should be 1, 3, 3, 1. The next one should be 1, 4, 6, 4, 1. You may say, well, what is the use of such construction? Well, look, once I make this identification, I see that I can write this as 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2, and this is 2 to the power of 3. So the expectation that I have is that if I was to add the elements of this row, right, the sum should be 2 to the power of 4. But now that may require some inductive argument, which I wish I could avoid. So let's do the following. Now that we're talking about Pascal's triangle, there's an associated theorem, the binomial theorem. And it states that under certain circumstances about x and y, all that matters is that I should be able to, that x times y is the same as y times x, so some commutativity there, is that this is nothing else but the sum ranging from 0 up to n of these coefficients. But then, look, if I specialize this, I would say set x to 1 and y to 1. So 1 plus 1 to the power of n is nothing else but the sum ranging from 0 up to n of CNR times 1 to the n minus r times 1 to the power of r. Simplifying this expression, it becomes the sum ranging from 0 to n of C of nr times 1. So I get that 2 to the power of n, which is 1 plus 1 to the power of n, which is nothing else but this sum. But this sum is the one that we got here, so I'm just going to replace it. This is C n 0 plus C n1 plus C n2 all the way up to C n. And well, that finishes the problem. Take care.